Oh, let's make sure we're all squared away. Hello, 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 hello. Hopefully everybody can hear me. What's going on, everybody? Go adjust my mic real quick. Hopefully all is well. Let me know in the chat real quick if everybody can hear me and all that good stuff. We're going to be hopefully diving into MPLS. So what's going on, everyone? Hopefully everybody is well. So this stream is going to be more geared to those of you that are focusing on the in the RC course, so more of the advanced networking skills that are attached to the CCNP Enterprise certification. So one of those topics on the blueprint is an understanding of MPLS VPN and all that good stuff that goes along with it. So we are going to be taking a look at how MPLS VPN works. We're going to be taking this little guide down here in the bottom portion of the topology will be our MPLS service provider. So we're going to go through and get all of the config up and running for it. There's a number of things that we have to do actually. We're going to have to go through and configure the, validate the Igp routing, which should already be working. Then we'll have to go through and validate the getting LDP up and running. And then once we validate that LDP or label distribution protocol is working and get it squared away, then we're going to have to dive into getting BGP working. So we'll get BGP operational and squared away that way. And then we will focus on doing the Vrf config. Once we have the Vrf config in place, we'll be able to transition into the PE to CE routing and all that good stuff. So yeah, so hello to you as well. So yeah, if you're watching this in a live format, go ahead and ask any questions you'd like regarding MPLS. I'll do my best to answer them. So we'll be taking a look at how all that type of stuff comes into play as we're moving forward. So let me talk a little bit briefly about how MPLS works and what it's really designed to, what its job is designed to solve, and why customers look at it. Because if you understand the why, then that makes it easy to justify the implementation. There's some topics out there that I have personally struggled with, seeing their validity and their use cases, and so I'm so only because of the fact that I haven't seen a lot of legitimate use cases and reasons. One of those is going to be for example, Lisp. So it's a topic that I know I need to dive deeper into. I know I generally understand it, but I'm like, I don't know anyone running it or why anybody would. So other than to use it in a software-defined access environment, that's just my take on it. So a lot of that has to go with, I don't see a legitimate reason to use it. So it is what it is. That's my personal view on it. So we're going to talk a little bit about how MPLS comes into play and all that type of stuff. So, and why people would use it. So a common thing that I see a lot of people or a lot of organizations having to rely on is connectivity in between their locations. So there's a couple different ways that you can do this. You have, say site 1, let's make that site 1, you have site 2, and you have, say, site 3 and site 4, right? And you need to interconnect them somehow. Well, there's a couple different ways that you can do that. You can do that with, IPsec VPN over the internet. That's one way. But what if you need to provide some sort of advanced capability? Let's say you need to be able to provide an SLA or service level agreement or quality of service or something like that. You really don't get QoS with the internet unless you're reaching out and covering or diving into a ITSP like an IP telephony service provider. No service provider that's running pure internet that I'm aware of supports QoS. So because of that, there's really no way to guarantee that your traffic is going to be prioritized. So what is exactly labeled unicast? Yeah, I'll dive into that. Labeled unicast is a different concept than LDP, but I'll talk about that briefly when we get into how that works. But it's BGP is the labeling mechanism and not LDP. But we'll take a look at how that specifically comes into play. Well, actually, we won't be doing it in this video. Labeled unicast is a way for you to use BGP to do labeling as well, but that's going to be more of a let's see, you could use that, you could use it internally if you'd like, but the only time I've ever seen labeled unicast used is with some sort of inter-AS VPN, like inter-AS option B and C, because I don't think I've ever tested labeled unicast in option A. At least I've never done it. But that's basically how that comes into play. So you have a provider. Insert whatever name you like, right? So we'll use ISP1 for generics. What I would do is I would build a network around. This network has to be built somehow, right? And then you would peer to the provider network, and then you would sit there and you would advertise routes here and advertise routes here, advertise here and here, and then the site 2, 3, and 4 would get learned here. You'd have 1, 3, and 4 here. You'd have 1, 2, and 4 here, and you'd have 1, 2, and 3 learned. So the idea is to be able to exchange route information with all of your locations with a common provider. So it gives you a lot of flexibility in terms of the operations. So massively scalable. I have a lot of customers that I've worked with in the past that run MPLS VPNs because of the fact that it gives you that ability to prioritize traffic and use QoS and things like that. So there's a couple building blocks that you have to understand in terms of how to get MPLS. Oh, wow. Wow. So, yeah. So we have a troll in the chat. His name is Paul. Paul is a longtime friend of mine. Paul is referring to Tag Distribution Protocol, which is your predecessor to LDP. So, yeah, thanks for that, Paul. So, yeah, good stuff. There's some building blocks that we have to understand in terms of how to get this working. So, in order of processing that you want to do in order to get this up and running and validation, the first thing is going to be IGP. Make sure it's working. Now, yes, you can do this with static routing, but nobody in their right mind is going to do that. So IGP is going to tie directly into LDP, or Label Distribution Protocol, which is the open standard version, and not the TDP, as my friend Paul has so eloquently put in there. So you're going to get these two running. So you're in the IGP portion of things, you're going to run either OSPF or IS. I can't write today. IS. Can you run EIGRP or RIP? You can. Any IGP can work. Would you run RIP or EIGRP? No, you wouldn't. And the main reason for that is because if you want to scale MPLS to any decent size or any complexity, OSPF and ISIS are really going to be the underlying protocols to use because they're both link state routing protocols, and they support extensions. So with OSPF, you can use the opaque LSA. And I'm not going to dive into MPLS traffic engineering in any real detail, but then you also have IS to IS has extension TLBs, uses a type length value. They could be used for MPLS traffic engineering. So you can help be more specific in the network and that you're forwarding bandwidth reservations and take a particular path through the network, that type of stuff. So once you have your IGP deployed, so OSPF, we're going to be rolling with OSPF. We're going to enable LDP on all the interfaces running OSPF. So it'll be a quick, underneath the OSPF routing process, will be the command. So the command will be MPLS LDP auto config. Some reason my pen tool likes to mess with me. Auto config. You get that up and running. That's going to allocate labels. That's going to form LDP adjacencies and stuff like that. LDP is very IGP-like in the way that it works. There's a UDP discovery property of it, where you're going to find another LVP enabled device, and you're going to configure that, and you'll discover your other LVP neighbor. And then you also have there's a TCP component to LVP as well, which is going to be forming loopback to loopback, here to here, and that's going to do the actual label exchange. Yeah, I agree 100% with Paul's comments, because I have tested that out just to see what happened, and it's not a smart move. So you have that. So UDP for discovery, and TCP for the actual label exchange. So both use port 646 for communication, in case anybody was curious about that. And then once you have that squared away, you have basically the underlay, if you will, configured. There technically is no overlay here, because everything you're routing through the provider versus over the provider. So the underlay is it's strictly underlay in this particular design, unless you want to run an overlay, which you could. Once you have IGP and LDP, there's a couple different ways that you can move to the next step. So this is always going to be the first step. The second step, third step, and fourth step, technically there's a fifth. The second step and the fourth step are, you pick and choose what you want to do. But normally the way that I do it, just so that I don't miss any steps, is going to be the BGP config. You do your BGP configuration, and then once you have your BGP config up and running, then you'll dive into your VRF config. The VRF config is necessary for you to generate the labels for the routes that you're going to learn. You have the next option is going to be your PE to CE routing. So you're going to peer with whoever you're connecting to, and then whether you use BGP, OSPF, EIGRP, ISIS, RIP, static routes, doesn't make a hill of beans difference which way you go. It just pick one and go with it. And then lastly, you have the route advertisement. So you can 100% advertise routes from your internal network into the service provider core, and it'll propagate, and it works out pretty well. And that's basically what ends up happening. Now with BGP, the way that this will work is you could do this in a full mesh design. So we can either do a full mesh or in a route reflector. Full mesh is not smart, because just like configuring static routes for LDP doesn't make sense, you wouldn't do a full mesh with BGP. You could, but again, it doesn't make sense. You would actually use a route reflector design. We have two route reflectors here. We have one here, and we have one here. One is regular iOS. The other one is going to be XR. We're going to do both. We'll get that squared away. So those of you that are looking for a little bit of service provider to dive into for, say, the CCNP service provider, this is definitely going to float your boat there. Then, and what you do is your provider edge devices, so your PEs, form connection to the route reflectors through BGP, and everything works that way. Now, when you're doing your peering here, you're doing it through one address family, an address family of VPN v4. Now, there are other address families out there and available if you want to use them. Another one that's commonly used in the internet is called IPv4 unicast. Is there a whole lot of difference between VPN v4 and IPv4? There's a major difference, but there's also some very similar. There's some similarities as well. So, for example, when you take a look at how IPv4 unicast works, you're simply forwarding IP unicast. When you're dealing with VPN v4, you're adding in labels so that traffic can be forwarded through the MPLS backbone. We're simply looking at simple MPLS, nothing fancy with A or B. Enter AS option AB? No, we're definitely not looking at option D. Definitely not looking at that. I have a video on that though if you want to take a look. So once you have your route reflectors to your PE router config, so that's basically what this is going to look like here. You set up a full mesh there, and then you set up a full mesh here of your connections like this. Now you'll notice that we're not doing a route reflector to route reflector pairing. We won't be doing that. You could, but we're not going to. That's a little bit more of an advanced design. I'm trying to keep things super mellow here in the setup. Now the next piece that's probably the more complicated part for anyone that's transitioning into the CCNP world, especially if you're coming from like CCNA and you're diving into VRF, you probably have a general understanding of how basic dynamic routing works. So you can turn OSPF on, you can turn EIGRP on, maybe you can advertise a couple of routes, and you can get some EIGRP routing to propagate. But VRFs are probably the biggest hurdle for those of you that are just starting out learning MPLS. And the reason why is because you're creating a whole new routing table. So for example, with the VRF, stands for Virtual Routing and Forwarding. Think of this like creating a new VLAN. So it's similar to a VLAN, where when you do this, you're creating a new user-defined routing table, or RIB, routing information base. And basically what that does is the VRF is what provides the separation for the customers. So I can have multiple VRFs configured on my PE routers, and that's going to allow the segmentation of traffic from customer 1 to customer 2 to customer 3 to customer 4. So when we dive into those more advanced concepts, like for example doing a VRF aware dynamic routing protocol adjacency or peering, depending on if you're using OSPF, EIGRP, RIP, or if you're using BGP, those are the type of configurations that would need to be VRF aware. Are we going to be doing anything VRF internally in the service provider core? No, we won't. And we're not going to be dealing with any MPLS TE in this video, at least not in this session. We might do that in a later session. But when we start diving into the VRF, it's created locally on the provider edge. We're only going to be creating one VRF, a VRF1, so we'll call it ONE or 1, and we apply that to the interface. So this gets applied here, and that's going to allow these devices right here to form peerings with these devices. So we're going to have a number of VPN peerings that we're going to set up in order for the communication to happen and all that type of stuff. Now, the VRF in and of itself has a couple of attributes that we need to understand before we start diving into the config. The first attribute of the VRF that we need to know is going to be the route distinguisher. Now, what is the route distinguisher? The route distinguisher is a 64-bit, so 64-bit, it's a 64-bit prepended BGP extended community value. So it's a BGP extended community. Now, what is it used to do? What it's basically used to do is make routes on a per customer basis unique in the service provider core. So when you are configuring the provider edge routers with the VRFs, there's a couple things that you have to do. The first one is create the route distinguisher. Because if I was to just have peering set up from the provider edge down to the customer edge and do a bunch of them, and set the BGP peerings up and everybody's happy and the customers start propagating routes, well, what if customer 1 is using the 10/8 range, and then customer 2 also is using the 10/8 range, and they're peering to the same PE routers, they are riding through the same backbone? How do you provide uniqueness on a per customer basis? And the only way you can do uniqueness here is by adding some variable in that will globally separate the customer traffic from one another. And the way that that's done is with the route distinguisher. Now, there's a couple different ways that you can configure it. We're going to be doing it the easy way, and we're going to be using, since we're using the VRF number of 1, we're also going to be using the route distinguisher of 1:1. Now, some people will use the autonomous system number. Some people will, like, for example, I'm sorry, you wouldn't put it there. You'd use like the autonomous system number of the customer inside of that. You could use the loopback address of the provider edge router and things like that. Those are fine if you were to dive into like the CCNP service provider side of the house, or if you have any intentions of looking at maybe CCIE service provider. I've done some crazy looking designs in the past and some different scenarios that I've labbed up and things like that just to see the differences. There are differences between doing a, say, example, a 1:1 1:1, which is what this would be. So this port right here is 32 bits, this part right here is 32 bits, and then you can create that, and then there's another colon here actually, and this piece right here is put in front of whatever subnet is being propagated. So for example, if you're doing 10.1.1.0/24, this would be unique, and let's say for example we had customer 2. If we had C2, we might have 2:2, and they might also be propagating 10.1.1.0/24. Our route distinguisher is what makes that route unique in the provider core. That's why we need that. So that's a simplified explanation of the route distinguisher. And that's a pretty straightforward definition of how it works and why it's needed. So in the event that you want to modify this to be a different value other than the 2:2, you can use whatever supported formats are available to you, but your outputs may look a little bit different than the ones that I'm going to be showing you once we get this configured. That's okay. I actually encourage you to play around with a couple of the different variables so you can see what they look like in case you're presented with a question in the exam and they're like, you get an output and you're like, well, I have no idea what this is saying. So I'm not going to show you here, but I have created MPLS VPN Layer 3 VPN videos on this channel. If you were to go look at them in the Service Provider playlist, you'll see what I'm talking about when you start getting into the more advanced configurations. Well, okay, so Paul's fun fact, yeah, I would never use OSPF in production as a PE2C routing protocol if I had my way about it. I don't know any providers that do. Every provider I ever work with runs BGP, but I digress. The other part of here that needs to be understood is going to be what they call the route target. The route target, think of this like an access list, and this is going to help determine which PE routers you're going to exchange routes with. Because we're going to have 4 PE routes. We're going to have 1, 2, 3, and 4. Right? So we have 4 PE routers that we can configure or work with. And each one of them is going to need to be able to receive routes from the other PE routers. Now, the way that this works, like I said, think of like an access list. And if the way that they're configured is more of a, does this line up? And when I receive a value in, let's say I get a route update from a route reflector, and I get an incoming route target value, if that route target value does not match something that I'm willing to import, then I'm going to drop it. And this is how you have the import and then you have the export. The import is going from the VRF to VPN. Hold on, let me back that up. Let's do BGP VPN v4. That's you're taking it out of the customer's routing table and putting it into VPN v4 to propagate it to the route reflector. The route reflector will then send it upstream to the remote PE. The export is taking out of BGP VPN v4 and putting it into the VRF. That's basically how that works. So when you want to take a route from VPN v4 and bring it into your routing table in the VRF, then you would do an export. Now, when you configure this, there's a couple different ways that you can do that. You can configure one. Normally, you're only going to configure one export type on a per VRF basis, and that'll be you pushing routes from the customer's routing table into VPN v4, but you can have multiple import rules as well. So it's kind of cool in how that works. So oftentimes you'll have one export rule, and then you'll have n number of import rules. And the reason why you would do that is because you could have potentially a lot of provider edge routers that you want to receive routes in from. And there's nothing wrong with doing lots and lots of entries because it gives you more granularity. However, we're going to be doing, just like we did with the route distinguisher with the 1:1, we are going to do 1:1. So we're going to type in the command route target, and we're going to use the command both, which is going to configure both the import and the export at the same time. RT both, and then 1:1 to keep it really, really simple. Once we have that in play, then we'll be able to receive routes from everybody else. And that's basically what it's going to look like. And I'll implement a couple of quick debugs, so we'll see how that process comes into play and things like that. So that's how that piece comes into play. So I'm actually running out of room on my console, so let me go ahead and scroll down a little bit so that we can, let's see here, there we go. So we have a little bit more room to work with. So let's wrap up this piece right here. So we have a little bit, we have a couple more details we need to go over before we dive into the config. The config isn't going to take us a ton of time. That's why I'm taking my time to explain it ahead of time. So the next piece, number 4, is going to be the PE to CE routing. The PE to CE routing, we're going to be using BGP. And when we go to configure this, we're actually going to go underneath the VRF. So we configure BGP. In this case here, it's going to be 65001 is going to be our autonomous system number. And then what we'll do is we're going to come in here, we'll type in the address family. Now, facing the customer. So this is going to be a PE to CE peering. We're going to have to, and this will be done via unicast. Okay. We'll do address family, IPv4, for some reason that didn't look right, IPv4, unicast, and then we'll specify the VRF of 1, all caps, and then underneath here we'll be able to type in the remote AS config and stuff like that. So that's basically how that'll come into play. Now, what's cool about iOS routers is as soon as you form that BGP peering, everybody's happy, right? The BGP peering is formed. You form the BGP peering on the CE side or the customer premise equipment. You advertise a couple of routes. Bada boom, bada bing, bada boom. You're in play, right? On iOS XR, things are a little bit different, and we are going to be doing this on XR, so I'm going to give you the heads up on it. On XR, when you're doing any type of eBGP peering, and this applies to every address family that I've ever played with on XR, you need to have what they call as a route policy. The route policy, think of it like like a route map, where you need to go in and configure a permit statement. Like if you're to go into a route map, call route map permit, and then underneath that, just hit the enter key, and then exit out. If a route map has no entries in it, it automatically is a permit all. And you are going, like, if you were to configure an extended ACL and go underneath the extended ACL and type in permit IP any, it's matching on everything. So it's just going to allow traffic to flow through it. Route policy needs to be done the same thing, but it uses the term pass instead. You give it a name, so we'll call it RPL underscore BGP. And then what we'll do is when we go to configure a PE to CE routing peering, that's eBGP from the provider edge to the customer edge, we'll attach the RPL underscore BGP both inbound and outbound on XR. And that'll get us the route advertisements to go back and forth, and we'll be able to exchange routes and things like that. Now on the customer side, we're also going to have to configure this. So we'll have to go underneath the customer's environment. We'll have to set up BGP, and then what we'll do is we'll advertise some routes. We'll use some network commands. We'll do a redistribute. We'll match on a couple of interfaces and stuff like that. So be a pretty straightforward configuration. So if you guys have any questions as we're going along, as I as I dive into the config, let me know, and I will do my best to try to answer those as we're going along. But that's basically the long or the short of it. I'm going to go ahead and clear the screen, and we're going to go ahead and pull up Secure CRT and get this show on the road. I believe it's not that one, it's this one. So let's go ahead and dive into this config. I'm going to begin the process. First thing we want to do is we have to validate the Igp routing. So on router 9, which happens to be a provider edge router, iOS 9, iOS 11, iOS 12, and XR27 are all provider edge routers. So we're going to do a show IP route OSPF. And we want to make sure that we have the loopback addresses of those devices in the network. So I've got 11, I've got 12, I've got 27, which is great. I also have 1 and 2, which happens to be our route reflectors, which is 1 and 2. So they're working as well. So if I was to go to ping 10.1.0.11, sourcing from loopback 0, I should be able to ping it. And if I do a trace route to that same destination, I should be able to reach it in the data plane. And there we go. I haven't tested NXOS with MPLS VPN, so I couldn't tell you. You'll notice that in the flows that we get equal cost multipath. So we have multiple ways to get to the destination we're trying to reach, right? So that will also mean that LDP will be able to use ECMP. So a note that was asked about earlier, if we're going to be taking a look at MPLS traffic engineering. We're not going to be looking at MPLS TE in this video or in this session, but MPLS TE is not ECMP aware. So you can only take one tunnel when you go to configure it. You can have backup tunnels and fast reroute implemented, but you can't have equal cost multipath with inside of your MPLS TE tunnels with traditional MPLS TE. If you're using segment routing and things like that, that's a different story because you're not using RSVP in order to figure things out. But I'm going to go up here to router OSPF1 or do show run section OSPF. I think it's 65001. Yeah, so router OSPF 65001, and we're going to use the command MPLS LDP autoconfig. It's a one-liner, so we're going to go on to 10 and configure this as well. Router OSPF 65001 MPLS LDP autoconfig. Do show history. Oh. Yeah, unfortunately that command won't carry, so that's okay. We'll go to 11, do the same thing. Router OSPF 65001 MPLS LDP autoconfig. Now there are other ways to configure MPLS. You could go to the interface level and type in IP or MPLS IP, and that would work as well. I'm not going to do that because I'm just not, because I would have to enable it on every interface. On XR, we don't really have much of a choice, so I'm going to leave that for XR, trying to minimize the amount of config that I have to do, because I have a lot to do in a relatively short period of time. So router OSPF 65001, and then we're going to type MPLS LDP autoconfig. There we go. So that piece is done. Now we're going to jump over to XR26, which happens to be in the core here. And we're going to go ahead and log in Cisco. We're going to go to global config. I'm going to type in router OSPF 65001, and I'm going to type in MPLS, so you can type the command in here, MPLS LDP autoconfig, but if you're trying to be specific per area, you would be better off, because if you don't want to enable MPLS LDP, or if you don't want to enable LDP on all the areas that may be running inside your environment, you can be selective. So you can do this, or you can type in area 0 and MPLS LDP, but maybe you don't want to enable it in area 1 for whatever reason. But that option is there as well. So we have that. And can the tech used here be summarized as a MPLS OSPF multi-protocol BGP? I suppose you could say that. I don't know if I would use that specific. I mean, I get you could, I suppose. The only reason I'm hesitating on that is because, well, yeah, you're trying to concatenate all of the technologies into a single use case or way of describing it. So I suppose that would work. Then we also have to go underneath MPLS or MPLS LDP, and then we have to go, and I believe the command is going to be, we have to create the interface here, and it's going to be a lot of them. We have multiple interfaces, so interface gig 00000, and then we're going to do gig 01, gig 02, gig 03, gig 04, and gig 05 and then gig 06. And that's basically how that would come into play. So if we were to go ahead and do a show config, I mean, there's a lot of individual command. This is no different than going on to a iOS router and typing in the command MPLS IP at the interface level. I'm going to go ahead and I'm going to copy that, and then I'll copy the first couple of, let's see, 0, 1. I'll copy this, and I'll go ahead and I'll commit. And then we should, let me back out of here and type in log neighbor. I'll log neighbor, and then I believe I'm already, go ahead and commit that as well. So if we were to jump out here and do a show route OSPF, we should be running that and show MPLS LDP. What is that command? Show MPLS LDP forwarding. There we go. So it is working, but we are, because we're 26, we're getting a lot of implicit null, and I'll talk about that here in just a minute. A lot of other devices don't have MPLS running at the moment. So we're going to go over to 27 and get him configured real quick. Cisco, go to global config. We'll go ahead and dump these few commands in here, gig 00 and then gig 04. And then we're going to go ahead and commit that config. And then, so that gets all of our PE routers and gets all of our provider core routers. So provider core routers, just a quick touch on that, is PE routers are going to be able to connect to customers. PE routers, or provider core routers, only connect to PE routers and other PE routers. So PE routers will connect to P routers or PEs. So provider core doesn't touch the customer at all. So just keep that in mind. So let's do on 27, we'll do show MPLS LDP forwarding. And we're starting to get labels brought in. So we're looking pretty good there. And there's a couple in here where it says implicit null for 10.10.11. 10.10.11. The reason why we're seeing implicit null, so the reason that comes into play is because who we're peered to, in this particular case, 26 and 10. In this case here, we're learning that from 10 for this specific route. We'll look at this. We're learning that from iOS 10, and because iOS 10 is directly connected to this particular subnet, it's basically telling XR27, you know what? Don't send any label, or don't forward traffic to me with a transport label, because there's going to be two labels that we're going to see. The first label, the top label, is going to be the transport label, which is going to get us from one PE router to another PE router. And then once we get the BGP process configured and everything else going, the next thing we're going to have to do is form the VPN-v4 peering from the route reflectors down to the PE routers. Once we have that in play, then we'll be able to go forward and start learning routes, do the PE to CE routing, all that type of stuff. But what you'll end up getting is, in order to get from, say, iOS 9 to iOS 12, for iOS 46 to be able to talk to iOS 18, or anything sitting here on switch 40 right here, what you'll end up getting is the transport label will be used to get traffic from iOS 9 to XR27, or iOS 9 to iOS 12. There's going to be another label that's going to be allocated through VPN-v4 BGP, which will be the data label, or the bottom label, or the VPN label. The VPN label is how traffic is delivered to the provider edge, and how it knows which particular VRF aware interface to send the traffic out towards. And it's actually the BGP process that assigns that. For example, when router 46 advertises a route to iOS 9 on gig 0/1, that route learned will be allocated a label from the BGP process, and that label will be sent up to the route reflectors. The route reflectors will go ahead and send that down to all the PE routers. The PE routers will then know which VPN label to associate to it, and then know which transport labels to associate as well. The transport labels are going to be used in order to reach the provider core routers, but in the event that we need to send traffic towards another hop inside the MPLS core, we're going to need another transport label. So transport labels will change on a per hop basis. You may see them be the same, but you might see repetitive labels in the flow. That just happens to mean that multiple routers are using it, but they're locally significant to the router itself. So not that big of a deal. So we have that in play. So I'm also going to enable on Route Reflector 1, I'm going to enable MPLS here as well. So we'll type in router OSPF 65001 and SPF. For some reason I can't spell. And we'll type in MPLS LDP auto config. And then on Route Reflector 2, we're going to go ahead and log in here. Go to global config, router OSPF 65001. We're going to type in area 0, MPLS LDP auto config. Exit out of that, and then MPLS LDP interface gig 00000 and gig 1. And then we're going to do a log neighbor. And then we're going to go ahead and commit. And so we should see label adjacencies pop up there. Actually, let me type in, yeah, it should pop up because we're doing logging. So we have that. So now that we have everybody enabled for LDP, let's go back to 9 and let's validate that this is working. So we're going to do a show MPLS LDP forwarding. Show MPLS forwarding table. And we see a lot of stuff. This pop label is the same thing as that implicit null, just a different term. So we see all that. So we're going to do it, and we can see that we've got 12 in here, which is where we're going to go. I believe that's where our last one was, to 11. So we're going to trace route, but you can see that we're using an MPLS label to get there. So we're using label 19 to get to 10. That's taking this path right here. We're using label 24,005, which is taking us to 26. Now, iOS XR uses a different label range. They start off with the LDP labels at 24,000 and go up to 1,050,000, I believe is the value. The reason why the values 23,999 and below aren't used is the first 8,000, so 16,000 through 23,999 are used for segment routing. So there's an 8,000 label block known as the segment routing global block. That will be used. That uses those ranges, and 16,000 and below are, for whatever reason, is reserved. I haven't been able to find good documentation as to why, other than the fact that they're reserved. So we have that, and then label. I believe they start off here at 16. So 16 and below are, I'm sorry, 15 and below are reserved in MPLS or just in LDP. There's a couple of them specifically, like label 3 is used for implicit null. You have label 1, which I believe is the OAM router alert label, and I'm trying to go back, jog my memory as to what some of the other ones are, but not really terribly important at this point. So we have LDP deployed. The next thing we want to go do, and the reason why we need that rolling is we need to have the transport, or the backbone needs to be LDP aware. So we need, anywhere we go from any PE to any other PE, we need to be able to get there via a labeled path. So we have that part done. The next thing we want to do is go on to the route reflectors. I'm going to start on route reflector 1, and I'm going to enable BGP. So router BGP 65001. I'm a big proponent of specifying what address families I want to run, and not just let BGP kind of do its own thing. So I like to turn off IPv4 unicast, so no BGP default IPv4 unicast. So I'll have to manually turn on the address families that I want to run. So I'm gonna, since I only have 4 PE routers, I don't have a very large deployment. I could use a peer group, I could use a template, any of those configuration optimization options that are available. I'm not going to do that here. I'm just simply going to, no, I'll go ahead and I'll do it. So I'll type in neighbor, and underneath the neighbor command, we're going to give this, and we'll call this VPN v4, and then we'll call it peer group. So now we have that created. I'll type in remote AS of 65001. The update dash source is loopback 0, and that's pretty much all I need for right now. The route reflectors are going to simplify the amount of BGP peerings. They'll receive routes inbound from the provider edge router, so iOS 9, 27, for example, anything connecting to a customer. They'll take the routes that they learn from the customer, they'll send those as BGP updates to the route reflectors, and the route reflectors will then go ahead and reflect them down to any other route reflectors, any of the other provider edge routers, to let them know that there's new routes to learn. That's why. So the next thing we're going to have to go do is type in the address family VPN v4 unicast, and I'm going to come up here, and underneath the same command I'm going to type in route reflector client, and that's going to apply to any of the neighbors that we peer with. So I'm going to type in neighbor. In this particular case, it's going to be 10.1.0.9. Peer group is going to be VPN v4. And that'll automatically inherit the remote AS command. So do show run section BGP. In case you've never seen this before, let me show you what it looks like. So you can see we have, this is the peer group config right here. And then by typing that, associating the peer group, we automatically associate these commands right here to it. The remote AS 65001 and the update source loopback 0. So we have that. So I get to come up here and I get to go and do this a couple more times. I'll do 11, I'll do 12, and I'll do 27. Just like that. Now I need to go underneath the address family VPN v4, and then I need to activate these adjacencies, or these peerings I should say. I shouldn't call them adjacencies because they're not. So I'll type in activate, and as soon as I activate it, automatically that route reflector client command and the send community extended for those extended community values that we need to send for the route target information and the route distinguisher, all that stuff right there is going to be propagated in that command right there. So I'm going to come up here and do 11, I'll do 12, and I'll do 27. There we have it. So if we do show run section BGP, the syntax is actually pretty straightforward, and I'm definitely simplifying it a little bit. So we have these commands applied. So because the fact that we have this peer group has been configured, and we're adding address family specific configs to it, the send community extended and the route reflector client will automatically apply to all 4 of these peerings. So the cool thing is, I'm going to go over to route reflector 2 and do the exact same thing. So over here I'm going to type in router BGP 65001, and I'm going to type in, I have to enable the address families here. So I'll type in address family VPN v4. Actually, I need to do IPv4 unicast first. IPv4 unicast, and then I also need to do VPN v4, because you can't run VPN v4 if IPv4 is not turned on. And then, so now that I have the address families configured, I'm going to be able to configure the neighbors. So XR is a little bit more modularized, so I can create the neighbor once, I can copy and paste in the configs over and over and over again. I'll type in neighbor, in this case here will be 10.0.1.0.9, remote AS of 65001, the update dash source is going to be loopback 0, the address family will be VPN v4 unicast, it'll be a route reflector client. So I'll do a show config. I wish iOS did this, because this would be super, super helpful. Same thing with Nexus. I'm spending quite a bit of time on Nexus lately with VXLAN, and I wish this command was available. So much of a time saver. So just dump that command in like that. Come up here, do 12. Dump that command in like that. And then we'll do 27. And we'll paste that command in as well. I'll do another show config. And we can see the config has already been applied. We'll go ahead and commit that. That'll take a couple of seconds for it to do its thing. Now, we haven't actually configured any of the provider edge BGP peerings yet, so we're going to go do that now. The cool thing about it is I configure it once, and I just paste it into 11 and 12 respectively, and then I can go to XR27 and do it. So I'm going to go to global config, router BGP 65001. I'm going to type in no BGP default IPv4. And I'll type in neighbor of 10.1.0. 1 remote AS of 65001, an update source of loopback 0, address family VPN v4. We're going to go ahead and activate it. So we're going to go ahead and we'll also do the same. Let me go ahead and exit out of here real quick. And then we'll go see that the peering's up. We'll type in neighbor of 10.1.0.2, remote AS of 65001, update source loopback 0, and then address family VPN v4. And we'll swap that 1 out for a 2. Now, do show run section BGP. This is why I didn't use this config, because you can see just from that 2 peers, you can see the amount of syntax. So I'm literally just going to grab all the syntax right here, and I'm going to go over to 11, paste it in, like so, and then on 12. And here in a very, very short period of time, route reflector 1 should start popping up peerings. Route reflector 1's got peerings popping up, and then route reflector 2 has peerings popping up. So if we jump out of here, we do a show BGP VPN v4 unicast all, or unicast summary. I don't need to throw that in there. We have all these BGP peerings up and running. So the next thing I'm going to go do is configure this on 27. Oops. Cisco. Go to global config, router BGP 65001. And then we're going to type in no BGP for address family IPv4 unicast, and then address family VPN v4 unicast. And then we're going to jump out of here and we're going to type in the neighbor of 10.1.0.1, remote AS of 65001, update dash source loopback 0, address family VPN v4 unicast. And you have to specify the unicast command here. You don't really have a whole lot of choice. And then we're going to go and exit out of here. I'll do a quick show config, because then I can just grab these few lines of config and then hit the up arrow to go to 2. 2 like so. Paste it in and commit. Give that a couple seconds and we should have a BGP peering to 27 as well. Alright, we'll have peerings to 1 and 2 here momentarily. 1 and 2. Boom, there we are. So show BGP VPN v4 unicast summary. We have our peerings are up. So we already have a bunch of stuff done and we're in really good shape. The next step that we want to go through and do is the VRF config. So I'm going to start this on iOS and I'm going to copy the config to 11 and 12. So there's a couple different ways that you can do this. You can run VRFs in just straight IPv4 mode, or you can run them in AFI mode, which is allowing VPN or IPv4 and IPv6. We're going to run it just for V6, or give the option for V6 if we want to. So it's going to be VRF definition and then 1. Now, by doing that, I've automatically given it the okay to do IPv6 mode as well. I'm not going to turn it on, but the option is there. So we're going to type in globally. I'm going to do a couple commands. And the reason why I'm going to do it globally is so that it applies to all the address families, so V4 and V6. So I'm going to type in RD, and I'm going to type in, you can see it's autonomous system number. You can do the IP address and a number, a 4-byte autonomous system number. So you can do that. Those are your options. So we're going to use the autonomous system number. I'm going to use 1:1. You could type in 65001:9. That would work. Or you could do 1. Or you could do, say, 10.1.0.9:1 or 65001. It's up to you on how you want to do this. Or you can use the provider or the customer's autonomous system number. You can use 65103. The choice is yours, how you want to do it. I'm going to use 1:1 for simplicity. I'm going to type in route target value. I'm going to specify both, and I'm going to say 1:1 as well to keep it really, really easy for the configuration. If you want to take it further and play around with those different variables, have at it. I'm going to type in address family IPv4 unicast. And if we wanted to do anything in here, we could. You can see that if we wanted to do unique route target values on a per address family basis, we could. So we can have two different topologies, one for v4, one for v6. If we wanted to do, my buddy Paul, I'm not sure if he's still here or not, but mentioned doing inter-AS option AB. If we wanted to do AB, we have to use this inter-AS hybrid command, which is a combination of using A and B, which is more of a service provider thing. If you want to do route exchange between two different service providers, that's how you would do it. But we're not going to do anything beyond that. So we're going to go ahead and exit out of here. Now, what I have to do is I have to take this config and apply it to the interface. So what I'm going to do is I'm going to grab Notepad real quick, and I'm going to grab the syntax. So I'm going to do show run vrf1. Yeah, you're like a rash. You just don't go away. Paul knows who I am. Actually, Paul and I used to work together, so I can make these snide comments, and I know he's gonna be like, meh, whatever. I know Paul. So that's the syntax. So what I'm going to do is I'm going to take that off screen and actually minimize this a little bit too. And what I'm going to go do is I'm going to apply this to the port. So interface gig 0/1, do show IP interface brief. Nothing is applied, which I knew there was. If you apply an IP address to an interface, it's going to get removed when you move it into a different VRF. Because if we go to interface or go in here and type in no shut, and then we apply an IP, so I'm just going to do one just for this, just for demonstration purposes. I'll type an IP address of 1.1.1.1/24. Okay, so do show IP do show IP route connected. We can see that 1.1111 is here, right? Now if I type in here the VRF forwarding of 1, it gets removed. And then if we look at the do show IP route, you can see gig 0/1's been removed. Then I can type in the IP address command here of 172.16.103.9/24. So do show IP route connected. It's still not here. So where did it go? Where's it hiding? Well, you have to throw in the command vrf1. And that's where it's hiding. You have to type in the vrf aware commands in order for this to work. So that's basically how that would work. So do show run interface gig 0/1. We can see that it's been associated to vrf forwarding 1, and we're in good shape. So that's the vrf config. So let me go ahead, and I've got this syntax right here. I'm going to go over to iOS 11, and I'm actually going to take this syntax right here as well and paste it right here. And I'm going to change the address. So this will be 102, and I'll just do 11.11. And then I will come over here to iOS 11. And I will take all this syntax right here, and I will paste it into here. And then we'll no shut it as well. I believe it's shut down. So that'll bring that interface up. And then we're going to do the same thing on here, gig 0/1, and I'll use 121 is the address. 121.12. Just like so. Copy, go over to iOS 12, same thing, copy, paste. And then we're going to no shut that interface. And that's pretty much, that's that. That's the VRF config for iOS. XR is a little bit different. We're going to go over to XR27 and get him configured real quick. We're going to use, we have several interfaces here. So I'm going to actually bring this up, and they're all going to belong to the same VRF. So I'm going to have three interfaces in the same VRF. So on here I'm going to go to global config. I'm going to type in VRF. You don't have to specify a definition because it does V4 and V6 out of the gate. I'm just going to type in 1. And then we have to define the address family. So address family IPv4 unicast. And underneath here is where we configure our route target values. So we're going to type in the import route target, and then we need to specify what we're going to import. We're going to import 1:1, and then I get to come over here and type in export 1:1. And I get to go show config. Now, XR will automatically put the syntax in the order that it needs to be there, and we can see that it's applied the way we need it to. The next thing we need to go to do is type in interface gig 00001, do show IP interface brief. Gig 01 is not configured, neither is 2 or 3. I'm going to go ahead and type in Vrf 1, an IP address here of 172.16.110.27/24, and no shut. And I'm going to go ahead and go up to the top here. I'm going to go to gig 02, Vrf 1. IP address here will be 127.24, and no shut. And then go to gig 03, which is the other one. Gig 03, we'll type in the VRF, the IP address, in this case here will be 101, and then we're going to go ahead and no shut it. So if we do a show config, we should have the VRF created right here. We're just IPv4, and we've got gig 1, 2, and 3 configured to be underneath the VRF, and no shutdown. I'm going to go ahead and I'm going to config that, or commit that config, and I'm going to, in XR, I'm doing show IP interface brief. The cool thing about it is, in this version of code, I believe it was in 6.0 code for XR, because I think I'm running 6.1. 6.0, sorry. So this version of code is when they came out with it, where they would actually tell you which VRF you're in. If you're on like 5.3 or 5.4 or some version older, then you'd have to do some finagling. So we're going to go ahead and finish this off. So the last thing we have to do with our configuration is configure the PE to CE routing. So that's where I'm going to start back on 9, and I'm going to configure that. I'm going to templatize it, and then I'll copy and paste it into 11 and 12 respectively, and then configure for XR with the route policy. So on 9, we're going to type in router BGP 65001. Then we'll have to type in the command address family, IPv4 VRF 1, and underneath here we'll come in and we'll type in the commands that we need to. So a lot of the same configuration syntax that you saw before. Type in neighbor of 172.16.103.46, remote AS of 65103, and that's it. That's all I need to type in. So if I do show run section BGP, give that a second to show up, you can see that the syntax is already good to go. So I'm going to go ahead and grab this notepad doc. I'm going to grab BGP here at the top, paste that there, and then grab just this syntax right here. Just like that. And now I get to go over to 11. And 11 is going to be, this will be 102, and I'm peering to 43. 43, and then the autonomous system number there is going to be 102. And that's pretty much all I needed to configure there. And I'm going to go to iOS 11, copy and paste that config there. And then on 12, it's going to be 121, and then I'm going to be peering to 19, and autonomous system number 101. Actually, I'm in the way. Let me go ahead and jump out of the way so you guys can see what I'm talking about. We have 19 over here, router 19, and we're 121. So we're going to copy and paste this syntax in right here on 12, just like that. Now let's jump over to XR27 and do this config here. I'm going to go to global config. First thing I'm going to do is create the RPL. So the RPL is going to be route-policy. I'm going to call it RPL BGP. I'll call it eBGP. and I'll type in, we have a lot of options. The entry we need is pass. We'll go ahead and exit out, show config, boom, that's our RPL. Pretty simple. We'll go to router BGP 65001. I'll type in VRF, in this case here 1. I need to enable the address family IPv4 unicast. And then underneath the VRF, not underneath the address family, but underneath the VRF, this is where I specify the route distinguisher. This is a key differentiator between iOS and XR, where in iOS you configure it underneath the VRF itself. In XR, you configure it underneath the BGP config, because that's where it's actually being used. So the route distinguisher value is actually used to help differentiate. Wow, my green screen went buggy there for a second. To differentiate the routes, it actually adds that 64-bit prepended extended community value. So in this case, your RD1:1. If we do a show config so far, I have that configured. That's all, and then I need to go and create the neighbor. So neighbor, in this particular case, there will be 3 of them. Let me go ahead and minimize this guy. And I need to peer to. Neighbor will be, we'll do gig 1 first. So neighbor is going to be 172.16.110.54. And then the remote AS for that command will be 65110. And then we're going to have to type in the address family of IPv4 unicast, and then the route dash policy of RPL EBGP in and out. So let's do a quick show config, and we're going to grab all this syntax for the neighbor. Actually, you know what? I'll grab the address family IPv4 piece. The neighbor and the autonomous system that we're peering to will be different. So I'm going to exit out 1 level, type in neighbor, 1 more level, neighbor, exit, neighbor of 172.16.100.17 remote AS of 100 65100. That's right? Yeah, 65100. And then we'll paste in the address family config. And then lastly, we will do the neighbor of 172.16.101.18 remote AS of 65101. The address family config, and commit that. Or let's do a show config real quick just to validate and make sure everything's correct. So 172.16.17, yep, 101, perfect, looks good to me. I'm going to go ahead and commit that config. It's a big deal to make sure you verify your configs. Don't just arbitrarily throw stuff at it. Make sure you're validating. So we have all that good to go. Now the next thing for us to go do is start setting up the CE side of the house. So this is like the last step. So we're going to start on, we'll start this on 17 side. So we'll work our way from left to right. So on 17, we'll do a show IP interface brief. And we're going to go ahead and I'm going to use the subnet of 10.100. So let's go to global config, interface gig 0/0, IP address of 10.100.1.17/24. We'll no shut it. And then we're going to come in here and type in router BGP, do show run section BGP. I should already be running BGP, which I am. I'm going to router BGP 65100, and then we're going to type in neighbor of 172.16. I need to enable BGP or configure that interface as well. 172.16.100.27 remote AS of 65001 address family IPv4 unicast, and we're going to go to interface gig 0/2. This is not Juniper. IP address of 172.16.100.17/24. And no shut it. No VRF necessary here on the provider or the customer side, considering we're just forming a BGP peering with them. And do show run section BGP. We're going to go underneath router BGP 65100, underneath address family IPv4. We're typing network of 10.100.1.0 with a /24 mask. So we'll get the first routes advertised. Now, one of the things that I'm doing here, do show IP BGP, is I've already got some routes learned here. One of the things that I'm going to have to do in the event that you're terminating a MPLS BGP peering and an internet BGP peering on the same router, and you don't want any of your internal routes potentially being leaked out to the internet, most service providers are going to block that anyway, is you would create a filter on your peerings. You can do that either as an ACL at the interface level or as a prefix-based filter on the BGP peering itself, where you're not going to permit and deny statements, and you can filter the routes out as you're doing that. We'll come back to that later on. Right now, I just want to get the BGP peerings up and running. So we have that going for us. So I'm now going to go over to 18 and get him configured. And whoops, while that's working, let me go over to XR27, and we're going to do a show IP route VRF1. And we have learned in a route, right? Although we've learned in several routes. We've learned in the public addresses as well, and we don't necessarily want them in our routing table. Now if I go to Route Reflector 1, I do a show BGP VPN v4 unicast all, I'll see those routes coming in, right? And I don't want all those routes coming in. That's why that filter I was just talking about, we would need that, because we have routes in here we don't need. And if I go over to say iOS 9, and I jump out of here and do a show BGP VPN v4 unicast all, I'm going to see those routes coming through, right? And if I show IP route VRF1, those routes are going to be in the VRF table as well, which when I form my peering between 9 and 46, 46 is going to learn those routes. And then we have a major problem, because then we have a potential route, potential loop, because 46, the 200.846 route right here, is being learned via iBGP and also potentially eBGP as well. So that could be a bad day. So you never want to allow your MPLS routes to leak out to the internet, and you never want your internet learned routes to leak in over MPLS unless you have a specific reason to. For example, maybe you want to leak internet over your MPLS VPN. That's a plausible use case, but so it is what it is. So just keep those things in mind. So next thing I'm going to go do is configure 18 real quick, considering I'm right there. Go to global config, and then we're going to type in do show IP interface brief, and we'll go to interface gig 0/2 IP address of 172.16.101.18/24. We're going to no shut that guy. We're going to type in router BGP 65101. Actually, let me get out of the way so you guys can see what I'm doing. 65101. Neighbor of 172.16.101.27. Remote AS of 65001. And then do show IP route. I'm going to go ahead and advertise the connected link. So network, type in address family IPv4, and type in the network command of 10.101.0.18 for right now, mask /32. I believe that's what I gave it. Yeah, so I'm good. So what you could do as well, if you wanted to form a dynamic routing process down here, like if you wanted to set up EIGRP and get 18 and switch 40 to be working, you could use EIGRP. You could do redistribution between BGP and some IGP and vice versa. But we're not going to do that right now. So do show IPBGP. We are learning routes and looking good. So eventually those will go live. Might just take them some time. I'm not terribly worried about it. The one route that we are interested in right now is going to be this guy right here. That's who we're interested in learning routes from, because that's the internal route. There we go. Now the routes are legit, and so we're in good shape. Now I'm going to go over to 19 and configure him. Go up here, host name is going to be iOS 19, and then we'll do, I don't know if I actually ever configured him. I did not. So we'll type in interface gig 0/1, IP address here 172.16.101.19/24. No, shut it, and then interface loopback 0, IP address of 10.101. What did I give 18? 10.101. Okay, that's right. 10.101.0. Let's see here, 19/32. And then we're going to go over to router BGP 65101, neighbor of 172.16.121.12, remote AS of 65001, address family IPv4. We're going to go ahead and network of 10.101.0.19 mask /32. And then that gets us we should get appearing here momentarily with that one. Assuming that I've enabled the interface. I have. Oh, I got the wrong IP. Interface gig 0/1. And I'm going to go IP address of 172.16.121.19/24. That's my mistake. Do show run section BGP. Make sure I don't have the wrong neighbor statement in there. So my validation is, there we go, that's correct. So do show IP BGP. So we're propagating that route. We're learning some other stuff in. Now I'm going to jump over to, let's see, let's go 43. Let's move that over to here. Let's go to 43. Show IP interface brief. And we already have the config or that good to go. So we're going to do show run section BGP. Up here, router BGP 65102. We're going to type in neighbor of 172.16.102.11, remote AS of 65001, and then we're going to type in. I'm going to do something a little bit different this time. Not going to use a network command. So we'll do the IPv4 unicast again, but and I'm going to type in route map permit, and then I'm going to router BGP, and I'm going to do 65102, and then address family IPv4, type in redistribute connected, and then route map permit. And so if I do show IP BGP, I should see that all of my loopbacks should be getting advertised. Hopefully. I may have to take this a step further and call the loopbacks from the route map. Route-map permit. And then match. Is interface an option? Yeah, interface. What are my interface IPs? I forgot. Interface, loopback 0. So interface match interface loopback 0, 1, and 2. Do show IP BGP. There they are. Okay, now they're getting advertised. So there we go. Next thing for us to go do is go over to 46 and get him configured. And that's the last piece, because actually, yeah, 43 is good. We're learning routes in from the other sites, which is what we want. And now I'm going to go over to 46 and configure him real quick. and we'll go ahead and do show IP interface brief here, do show IP route. We are learning stuff in from this side, and here's where I was talking about just a second ago about how the thing that we're going to run into here is you can see that we're learning in the 10102 routes from switch 43 in over our public BGP peering. So even though it's a simulated BGP route for internet, we're still learning it in that way. And that's where you have to lock that stuff down. So we'll go ahead and filter that stuff out here in just a second. We're going to have to deal with that sooner than later. So I'm going to go to router BGP. Do I have the IP address configured on the interface already? I forgot. 172.16.103. So router BGP, and I'm dealing with 65103. So 65103. We're going to type in neighbor of 172.16.103.9, remote AS of 65001, and then I'm going to go ahead and address family IPv4 and network command of 10.103.0.0 mask /24, I think is what it is. I'll double check here in a second. Do show run interface loopback 0. Yeah, that's what I thought. So then we can just come in here and do 1 and then 2 for the loopbacks. Okay, so now that we have that, we do a show IP route BGP. Whoops, I goofed that up. Let's go back over here. Let's do a show IP BGP. Show IP BGP here. So we're going to be learning a bunch of stuff in. So let me bring this down just so we can see everything a little bit better. We're learning in the 103 routes in from router 11, but my suspicion is if we try to reach anything, we're going to have a loop. So if I tried to reach 10.103, if I tried to ping 10.103.0.46, sourcing from loopback 0, oh, let's see what path it takes. I'm curious now, because I didn't think that was going to work, and we'll do numerically. Source. Oh, it's right. Trace IP, target IP is going to be this guy. I forgot I'm not on a router. Source IP is going to be, what's my IP address here? 10.102.0.43. Numeric display, yes. So it hits this 172.16.103. Okay, so it does take the MPLS path, which is what you want. So as I was talking about this earlier, you'll have a couple of different things to take a look at. We have the MPLS VPNs are working. So just in case anybody was curious, it is operational at this point. And you can see that if we look right here, this is our next hop. This is router 11 right here. And you notice this isn't a labeled path. This is straight native IP. And if we come down here to this next hop, we have 10.11.26.26, which is taking 11 to XR26. So this path right here going out gig 02 on 11. And you'll notice that it's got a labeled path. We see 24,001 and we see label 37. 24,001 is the transport label. So what the label we're going to use to get from iOS 11 to iOS 9. Label 37 is the VPN-v4 label that's allocated via BGP. So if we go to router 11 and we jump out of global, that was not cool. Let's look at 12. We'll do a show BGP VPN-v4 unicast all, and we're going to see some routes coming in. So we're going to specifically look at the route we're learning from 19, because that's who we're physically peer to. Look at this route. Look at the detail. So the way that you would determine this is you see this MPLS labels in and MPLS labels out. On the left side of this / you have in, and the right side you have out, which equals 34, label 34 inbound. So when iOS 12 learned the route from iOS 19 inbound, it went ahead and associated label 34. And then that information was propagated up to the route reflectors. So if we look at route reflector 1, We look at show BGP VPN before unicast all, and we specifically look at this route 10.101.0.19, we're going to see the out label. So on the right hand side of this output right here, we see the out label is label 34. And then when we get to iOS 9 and we do a show BGP VPN before unicast all, and we look at that prefix one more time, we're going to see the out label is 34. So we're going to use label 34 to get to where we got to go. So if we're on router 46 and we show IP route BGP, and we see, so if we do a trace route to 10.101.0.19, sourcing from loopback 0 numerically, we should see label 34 in the data plane. So label 34 gets us to iOS 12. Label 24011 gets us to XR26. So this path right here. And that's basically how this is coming together. So there's that. So MPLS VPN is working as far as we're concerned. Now there's a couple of little minor details that I want to talk about before we wrap up, because we've been going at this about 90 minutes. You'll notice that if we were to look at, say, iOS 19 and drop out a global config and do a show IP BGP route, show IP BGP, you'll notice that we are not learning in the 10.101.0.18 route. We're not learning that inbound right here. And there's a legitimate reason for this. So for those of you that are familiar with basic BGP, there's a, why am I all of a sudden having a brain fart as to what the term is? Loop prevention mechanism. Sorry, that's what I was looking for. There's a BGP loop prevention mechanism built in where if the AS that the route originated from is also my AS, therefore it's going to be more preferred to use another way of getting there versus learning the route in over the provider network. So the routes are actually going to get dropped. So if you're in the same same autonomous system number, so in this case here, they're both in 65101, right? So 18 and 19 are both in AS 65101. Because they're both in AS 65101, when 18 advertises the route, 27 propagates that down to 12, and 12 brings it back in, 19 actually receives it, but then drops it because it sees it in its own autonomous system. So as you see that, you're going to drop the traffic. There are ways of overriding that, and this is a very common thing that I've seen in production where companies will inadvertently, whether they didn't know or that's just the design that they came up with, use the same BGP autonomous system number on all of their branch offices. There's two ways to fix this. You can either A, on the customer side, type in the command allow AS in to receive the routes, or on the provider side, you can go through and have the provider override the autonomous system number that was learned from the customer and then advertise it as their autonomous system number. So in this particular case here, the provider we're pairing with is using 65001. When the provider uses the AS override command, they're replacing whatever autonomous system number the route was advertised with. So 18 and 19 are advertising their routes with the originating AS of 65101. When the provider learns that, they see it coming in as such, right? So if we look at Route Reflector 1, for example, and we do a show BGP VPN before unicast all, we see 18 and 19 being originated in 65101. You can see that right there. Because they're both being originated in 65101, then the provider receives that. The provider doesn't care. The provider they're just to replicate information. That's all that they're there to do. They replicate that information, and it's up to the customer's device to filter those routes out. You can receive them if you'd like, but in this case here, there's really no good reason for us to want to receive in a route that we have potentially reachability to via IGP. Now, where this really comes into play is you can do what they refer to as site of origin, and you can block the routes from being learned. So you can basically say, if this route was learned in, you can set site of origin outbound and say, if this route was also learned from the same site as I'm learning other routes from, I want to go ahead and filter those out. That's another option as well. So there's a couple different ways that you can filter it out. We're going to let it be the way that it is because it makes the most sense. Now, if I was using autonomous system number 65101 over here on iOS 46, for example, and I wasn't receiving any routes because it's the same autonomous system, I could do allow ASN on the customer side on the peering towards router 9 to say, you know what, I don't care if I see my same AS in the AS path list, go ahead and receive it. Or the provider could override it. XR will do that for us as well. If we want to do this, we could do with XR and we could do AS override. So that's just another option that we have available to us. So a couple of really cool things that BGP does for us out of the gate in terms of the operations and things like that. So that's basically what ends up happening. So what I'm going to go do now is I am going to look at doing some filtering because we're 17 and 46 are potential black holes or traffic issues for us because they're both peering to the internet and we don't want to have that. Any other routers that potentially also are peering to the internet and or maybe receiving routes from other routers that potentially are receiving routes from the internet, which means either iOS 18 could be receiving routes and could be propagating them back out, or 53 could receive a route inbound and accidentally propagate it out 54. Either way, you want to go onto the customer's device. You could do it inbound on yours as well, but because of the fact that I spent the majority of my career working in the enterprise space, I'd say a year or two, maybe 3 tops, was spent on the SP side of the house. So the way you would do this is you would only allow out whatever routes you have. So you could do this a couple different ways. I'm going to go with the prefix list, and it's going to be specific. So if I do show IP interface brief, we have 10.100. So we're going to do 10.100.1 is going to be the inside interface. So I'm going to type in IP prefix list, and the name of it is going to be BGP out, and I'm going to say permit 10.100.1.0/24. And then I'm going to create a route map. You can associate the prefix list to the BGP peering, but that doesn't give you a lot of granularity. So route map RM BGP out, and I'm going to say permit, match IP address and prefix list BGP _ out. And then anything else is just going to get dropped. I'm going to go ahead and go to router BGP. Oh yeah, you're right. Well, I think it should work either way, to be honest with you. So Paul's got a legit point, so we'll test it out. Paul and I used to do this all the time. Actually, we sit there and we debate stuff and let's lab it up and figure it out. So we're gonna do 65100, and then we'll do address family IPv4. Do show run section BGP. Neighbor. 172, what is that IP? 172.16.100.27. So 16.100.27. And we're going to do a route map. So the route dash map, and we're going to call the route map RM BGP out, and you would say outbound, right? So what we want to do is now do a show IP prefix list detail, see if we're matching on it. And at the moment we are not. Let's do a clear IP BGP star soft. There, now it's getting matched. So now what should end up happening is 27. Let's log into him real quick and do a show IP route VRF1, and we're still receiving 1, which is good from our peering. But so 2517. So we still need to. So Paul was right as well. We need to block these other routes. For some reason, they're still coming through, but those need to get blocked. So I'll go ahead and I kind of have to okay, fine, you were right. I was wrong. So it happens. So what we'll do is on 17, since we've got that traffic matched, which you would think that that would block the traffic. So he says not the routes you have, but the routes you are generating for others to use. Correct. So show IP BGP, we would have to block the 100, 5, 17, the 200, 846, and the 221. So we'll go ahead and IP prefix list BGP out, and we're going to deny, and we're going to say 105.17.0/24. We'll also deny, would be helpful if it would just automatically update the way that I want it to. And we'll say 200.8.46.0/24 as well as 2145.0. I think that'll do it. And we'll clear IP BGP star soft out. So now if we show IP prefix list detail, there we go, those routes are getting matched on. We go back to 27, hit the up arrow, and those routes, let's do a clear BGP star soft. BGP Vrf 1 star. Well, I don't want to clear with a hard reset, my grace. Well, I want to do a soft reset. Show clear BGP VPN before unicast. Is that not a supported command? Oh, there we go. Okay, I guess we have to do it the hard way. I don't see a way to do it soft, which is really weird. Star soft. See if that fixes it. I'm thinking that's weird. Why is it still allowing it to come through? Shut up, Paul. So it's weird that route. So coming in from 10.1.0. Oh, you know why? Okay, so I was able to filter. So part of my thing is I'm looking at it wrong. These are coming in from router 9. So I need to do the same thing on. So right now they're being learned in this way. So on 46, we'll do the same thing. So show IP BGP. And I'm learning these in from this guy, so I need to take these routes and deny them out, but permit everything else. So we're going to go and let's see. I want to permit only the routes that I am advertising myself, so the 103 routes, and then block these guys. So remember, it's an outbound update. So IP prefix list, and the name is going to be BGP_out, and we're going to permit 10.103.0.0/24, 1 and then 2, and then deny. Let's bring this down just a touch. Deny 100.2.16.0/24. We'll do 5.17. And then 200.8.46 and 2145. All right, so if we do a clear IP BGP star soft, show IP prefix list detail, let's say out. Why did that not trigger? That's not cool. Yeah, I mean, you could use AS path as well. That could work. So let's go back to 9, make sure that we're not receiving any of these routes in. And we are. Why are we still learning routes? Oh! I know why. It kind of helps. Hold on. So I was kind of a dork. It's okay. I make mistakes. All I did was configure the prefix list. I never applied it. So that's my fault. So we're going to create route-map rm underscore bgp out. Say match IP address in prefix list bgp out. And then we're going to type in router BGP 65103, address family IPv4, neighbor of 172.16.103.9, route-map, and then the name of it is going to be RM BGP out in the outbound direction. So clear IP BGP star soft. And then we'll do, there we are. Now we're filtering the routes. We go back to 9, hit the up arrow, and those routes should all be bye-bye. So we're only propagating the routes. Yeah, using regex maybe. I mean, regex could get ugly. I actually don't like regex, so yeah, I typically steer away from regex. But we have the routes in the routing table that we want, which is the ultimate goal, right? We removed anything we didn't want out. There are obviously much better ways of doing it. I'm just showing you a way of doing it. So, and my solution works. It's not the cleanest, but it gets the job done. So now we're just going to verify that we have reachability where we need to have reachability. So in 19, we're going to go over here and show IP BGP. BGP's got those routes, so we're going to go ahead and we're going to ping. Traces are actually cooler to do. So we're going to trace route to 10.103.0.46, sourcing from loopback 0 numerically. And we have reachability, which is what we want. I'm going to do another trace route to 102 and go to 43. We have reachability there. And then I'm also going to do a peering to 17. 17 will be 10.100.17. 17. Did I not advertise the right? Oh, Control-Shift-6. Show IP BGP. That's why. 10.100. It's like, I don't know how to reach that. There we go. So it's able to get to where it's got to go. So we have reachability everywhere. We have reachability to all the things. So that, ladies and gentlemen, is what I wanted to be able to demo. This is the type of stuff that you would need to be able to get. In the CCNP exams, obviously you won't be configuring this stuff, but if anybody is studying for the current enterprise infrastructure certification, this is something you're going to have to spend probably a significant amount of your time on. I know when I sat for the Route Switch Lab, I spent a good couple of hours getting all that stuff working. So just be aware of that. There was a question in the last stream that we did where the question was, what if we wanted to do a DMVPN over MPLS? Or what if we wanted to run some sort of IPsec or some sort of other overlay VPN protocol? And the answer to that question is, sure, it 100% can. And I've done it multiple times. Multiple customers I've worked with, I've done DMVPN over MPLS. MPLS is just another transport provider, no different than internet. So other than that, that is basically what it is that ends up happening when you start working with technologies like this. So can a person with CCR switch work in service provider ISP without having difficulty? How much different is it from? It's a lot different. So people that spend a lot of time in route switch are going to be able to get up and working pretty quick in a service provider world, but the SP world is its own animal. And I'd say that I learned more diving into SP about how actual routing works, especially BGP and IGPs, than route switch ever really made me work on. So I would say you'd be okay. I had no problem holding my own, but I definitely spent quite a bit of time working with the SP technologies because it made it that much easier to work with. I can definitely tell you that having spent a significant amount of time playing around with MPLS Layer 3 VPNs, all the different variations. This includes doing like carrier supporting carrier, all the major inter-AS options, traffic engineering. That's where it really starts getting into the weeds. When you start diving into segment routing, when you start diving into MPLS TE, because the average provider isn't going to just do this basics stuff. A lot of them are gonna do advanced routing. So you're gonna get into MPLS traffic engineering. You're gonna have multicast VPN, which is if you don't understand multicast VPN is that much more complicated. So there's a lot of things that you would have to know in addition to what you already know from the route switch world that the route switch world doesn't even touch. So there's a lot of stuff to come into play with it, and it makes it that much more. Challenging is probably the right term, but not difficulty. I mean, you can it's actually kind of funny. Paul and I worked on a couple of projects together where it was like he and I would sit down with a mutual coworker of ours that actually ran the company multiple times to work through routing designs because it was just they were that complicated, and we wanted to make sure we had enough eyes and ears on the project to make sure we weren't missing anything. What platform are you running? This is EVNG Community. I'm in the process of transferring over to Eve Pro. I've got an Eve Pro license. So now we're done with the technical stuff. Actually, hold on one second. Let me turn my green. There we go. That might help a little bit with some of the. I'm getting a lot of pixelation through the webcam, through the green screen, but. All good, man. So if we come over here to this topology, I've got Nexus 9Ks deployed, and I'm playing around with VXLAN and EVPN. I've actually got it working. I'm playing around with it. As a matter of fact, now I'm just showing off at this point. But let me show you this real quick. If I was to come over here and go to iOS 11 and do a ping from 10.1.1 to 13, I'm able to ping, and it's a VXLAN encapsulated ping, as you can see. So I've got VXLAN EVPN working and doing its job. It's actually been a lot of fun to play with. The only thing that I've ran into problems with is inter-VXLAN routing. I have not been able to get that to work I don't know why. I've watched a bunch of different resources online. I'm stumped. So I've moved on to like external routing with VRFs and dealing with VPC multipath and multi-homing via ESIs and doing multi-site VXLAN. I got a lot of stuff coming in the near future. So if you notice that what's the word I'm looking for? The post rate on the channel slows down is because I'm working at a bunch of other stuff, and it's time consuming to go through the material and to really learn it. So some pretty cool stuff. But this is Eve Pro, and one of the things I like about Eve Pro is if I make a mistake in my lab and I need to rebuild it for some reason, Eve Pro allows you to on-demand move your links around. So are the number of cores in your server enough for the courses you are studying? You'll never have enough cores, to be honest with you. I've got some pretty beefy servers, and they're all pretty much tapped out. So most of my servers are Cisco UCS C220s. Pardon me. I run C220 M4s and M3s. I think one is 24 CPUs, and then I have another one that's got 32 CPUs. It's an 8-core. I've got a 6-core CPU, dual Xeon 2650s. I've got another one that's got 8-core 2650s. So yeah, you'll always have CPU contention. CPU is going to be your bottleneck. I never have problems with RAM. RAM is always like a second. Like right now, this lab right here is running I think like 75 or 80%. I'm only using 40% of the RAM. So I'm always going to have CPU contingent. So, and the same thing with this one here. This one's starting to get big, a little bit long in the tooth. This one's run at 60%, 12% memory. So it's always a CPU thing. 100% a CPU thing. So, but it's cool because it gives me a lot of flexibility. So yeah. Pets is 96 core server. I'm actually looking at upgrading. I have an old IBM 3650 M2 with I think 22 cores, and I'm gonna be up. I'm waiting for after Christmas, and I'm gonna be after the first of the year. I'm gonna upgrade that. I'm gonna go buy another Cisco UCS C220, and I've actually kind of fallen in love with the C220s. They're older, but they're oldie but a goodie, and then deploy ESXi on that. I'm going to be upgrading from 6.5. 6.5 on IBM sucks. I'm always running into problems with it. It's actually this VM, this Eve instance is actually running on 6.5 for ESXi on the IBM 2697 version 2s. $100, huh? Okay, I'll have to look at that. So that's basically what I've been doing. So anyway, I've been going at this almost 2 hours. If you guys have any questions for me, let me know. Find me on Twitter. This is probably the easiest way to get a hold of me. I'm pretty active on Twitter. Find me on Twitter at RikerRob. Ping me on there. I will follow me there. I'm usually posting pretty consistently on there with any issues that I'm running into and stuff like that. So that's that. If you have a request for the next live stream, let me know. I will do my best to put something together for you. I didn't get any requests this last week, but I wanted to keep going through the flow of the CCNP Enterprise. So again, thanks you guys for hanging out with me today. It was a lot of fun. It was I like doing these things. I usually get a lot of interaction from a lot of people, which is cool. So again, we'll be doing next week Sunday at 2 p.m. Central Standard Time is my standard time to do a stream. I don't know what I'm going to do next week. You know what? I think I might dive into a little bit of FlexVPN, or I might do some VXLAN. So I'm also thinking about doing some like 802.1x and doing some ICE stuff. So I've been playing around with ICE a little bit lately. So anyway, we'll figure something out. Until next time, guys, thanks again so much for stopping by and hanging out with me. I will catch all of you in the next stream. Which server do you recommend for me? I need server for Eve. Cisco UCS C220, M3, M4. Look for 6 or 8 core CPUs. They seem to work pretty good. You can usually get a good deal for about, I don't know, $600-800. That's what I've been doing. So anyway,